I welcome you all again to the second session of day one. So good afternoon, everyone. We are having Professor Brajesh Kaushik from IIT Roorkee. He will be talking on Spintronics, perspectives and challenges. So I welcome you, sir, to the session.
Yeah, thank you. Thank you very much. Am I audible?
Yes, sir, you are audible. So let me introduce you to the audience. So Professor Brajesh Kaushik received PhD from IIT Roorkee in 2007. He joined Department of Electronics and Communication Engineering IIT Roorkee as assistant professor in 2009, and he has been promoted to professor since August 2020. He has been the member of various journals like IEEE Transactions, IEEE Electron Device Society, etc. And he has received many awards. Plus, he has research interest in the area of high-speed interconnects, low-power VLSI design, memory design, carbon nanotubes-based designs, FinFET devices, spintronics-based devices, circuits, and computing. So, without taking much time, I request Professor Brajesh Kaushik to kindly share his talk with all of us. Thank you, sir. Over to you. Professor Kaushik. Professor Kaushik, sir, you have to unmute. We are not able to hear you, sir. But we can see your screen. Let me call you.
Yeah, is it okay now? Yeah, yeah, perfect, perfect. Is it fine now?
Yes, sir. It is okay.
Yeah. Yeah, so sorry for the initial hiccups at at this point of time. But anyway, let us go ahead with the talk. So I would first like to thank Professor Arun Singh for inviting me over this lecture. And today, actually, I'll be taking you through one of the very interesting areas, which is really upcoming nicely. This is Spintronics, Perspectives and Challenges. So we'll be talking about Spintronics, which is really upcoming very fastly in last I can say 1 decade. And so maybe a decade ago things were more on theoretical aspects, but now it has come up to a status where everything is practically available, the memories, the logics, and many other things. And I think most of your computers also now have this non-volatile memories as well. So I'll be taking you through this journey, which is more towards spintronics. We'll be talking about some of the basic stuff related to memories, why memory is so important, and how it has unfolded with time over the years. Then we'll go on with fundamentals of spintronics, magnetic tunnel junctions, spin transfer torque, MRAM. So all these devices we'll try to cover as many as possible, and try to see how these devices can be really useful in ushering a new era of memories. So the evolution of memory technologies has been, it has been there from very long time. So evolution of memory technologies, if you see, it has been there in 1800s, early to 1900s in form of punch cards. Then in 1920s we had this magnetic tapes, and then we went on with the magnetic drums, mechanical memories, and you can see that after every 10 years the technology kept on changing. So 1940s we had William tubes during the time where tubes were very popular. Then we had this ferrite cores, hard disk, ultrasonic memory. Then we had this music tape, DRAM twisters, 1960s. Then we had this, bubble memories, and then came your hard disk, which actually, uh, helped us a lot in, reducing the size of the computing system as well. And if you see in 1980s, we had CDs, floppy disks, so all these things, started coming up. And as on date, CDs and floppy disks anyway have become obsolete, but they were, very much used at one point of time. So taking it forward in 1990s, we had this DVDs, which had, much more memory capacity. The flash drives, MMC, MRAMs were also, introduced during this 1990s. And from 2000 onwards, a very rigorous research is being carried out for flash, SD card, different kind of memory registers, spin transfer torque MRAMs, FERAMs, PCM, RAM, and all these kind of aux RAMs, polymer RAMs, many kind of RAMs actually have come up. Now this has been all possible because of this newer and newer materials coming up, researchers looking into non-volatile memories to be used for performance enhancement, especially in terms of power characteristics. So this has really unfolded very well over the last 1 decade or so. Now the memories have been very important component of any system. And if you see these memories are there, as of now, they are of different types available. You have non-volatile storage memories in form of HDD and flash, which have a lot of good capacity. Then we do have other kind of memories also, such as your DRAMs, then your caches in form of L2 and L3, L1, so on and so forth. And as you see this pyramid, which is quite interesting, you have non-volatile storages at the bottom right now. They are really known for their capacity. You do have huge capacity with these non-volatile storage RAMs, but then the other aspect of this is the speed, which is not much high. So the delay, access time that is there for accessing these memories is something around 1 millisecond, too high. And if you go up this ladder, you'll see that the speed actually becomes quite good as you move up. That is all because of the excess time, which is quite small as you move up. And also you see that the capacity goes down drastically as you move from non-volatile storages to other kind of memories, ALUs and flip-flops. So as you move into the core of any microprocessor or any processor, you need to ensure that that memory is really fast. And of course, all these things comes with certain cost. And you can see the cost as you move up from non-volatile storages to ALU or flip-flops, the cost per bit becomes exorbitantly high. So that is where actually it restricts too much of its usage also. So cost does come in terms of, especially the silicon area that it consumes. So most of you who are aware of memories, SRAMs can be made out using 6 transistors. It takes almost 6 transistors for realizing 1 bit of, memory storage using SRAM. Whereas when you talk about DRAM, it takes something around 3 transistors to 2 to 1, something like this. So it is all based on these different kind of memories that you have to make a choice and then use them in a system. So that is how things move. But of course, all these memories, especially DRAMs, SRAMs, all these kind of memories that we have been talking about, although they are fast enough, some of them have especially the good characteristics in terms of the storage density that is good enough. But then all of them are really challenged beyond 45 nanometer technology node. Especially why they are challenged. One of that is if you see into SRAM, it has high standby power consumption. So this power consumption, which is very high, you know, within this, if you see the leakage keeps on increasing 10 times with each technology node. So as you move on from 45 to say 32, 22, so on and so forth, every time your leakage power increases by almost 10 times. And that is really a big concern for the systems which uses huge amount of memory. And as far as if you see any system, almost 70% of the chip area is covered by these memories only. So and therefore it becomes really very important that if you want to reduce the overall power dissipation or if you want to improve the performance of any system, you need to focus a lot on these memories. Now let us come to DRAMs. They are also really facing huge challenges in terms of power dissipation. Reason being that they require huge refresh current, which is increasing, dramatically, and also it's incompatible to embedded kind of applications. Why? Reason being, most of the embedded systems which are sort of IoTs or maybe standalone system or maybe they are doing some computing at the edge, so they cannot afford to have too much of power dissipation. So there actually DRAMs really does not work well. Now the next choice is flash. Now, flash often you use for mass storages. Instead of non-volatile storages, you do use flash memories, but then they are not very fast. They are very slow, and also they have high write power consumption. And other than that, they have limited endurance. Also. Endurance means how many times you can write onto it, right? So then overwrite 0 1 0 1. So all those cycles are quite limited that you can put this um, flash memories onto. Now, when you come to power consumption in most of the portable and data center applications, it's really a big issue. And as far as the study goes, some of the countries may face huge power shortages all because of these data centers and the internet users that we have. So this may be quite surprising for people who are coming from India. We all may be surprised to know this because we do not have that much of internet users or maybe system users in India. But countries like Japan, they are seriously looking into all these data center power consumption issues also because the data center power consumption is increasing tremendously and probably it may equalize to what is being generated by that country in 2030. So whatever they'll generate, that will be taken up by these data centers only to keep up the internet users. And that is where it becomes really very important that these data centers where you're using these mass storages, they should consume as less as possible the power consumption. Now, as I said, data centers, they do have their own limitations. Now, if you see, the memory performance in these data centers is one of the key performance bottleneck. And I think most of these memories you have already made up using smaller and smaller devices, different kind of devices that are based on silicon. But then these memories do consume huge power, and therefore, from that perspective, the silicon industry is considered to be towards the end of its technology roadmap. You know, because huge power consumption, and there are certain other issues as well. Ahead with issues with nanoscale devices, of course, there are many other issues as well, especially with the conventional charge-based semiconductor devices. Other than this, it's really difficult to scale down the power supply below 1 voltage. You have to make a lot of trade-offs, maybe with delay, maybe with other issues. So all these things, it makes really difficult to scale down the power supply voltage below 1 volt. And of course, as I mentioned, rising leakage current is other big threat that we are looking into. So overall, it's really very difficult to design low voltage, low power, energy efficient circuits and systems using these current technology nodes. And if you see, especially with the memory technologies, you have high static leakage power with all these memory technologies. They have huge footprint area, as I mentioned. That SRAM requires something like 6 transistors, and if you want to make it more, better, maybe in terms of reliability and other things, you keep on adding the transistors onto it, and that way, your SRAM cells themselves becomes, you know, something like made up of 9 transistors or 10 transistors, so on and so forth. And when you talk about all these on-chip memories, most of them are volatile, and they are of low density, and also the cost per bit is also quite high on-chip memories, and they occupy almost 50% of the chip area. So each of these memories or each of these systems, they do have huge amount of presence in any of these chips as well. Now, when you talk about off-chip memories, so these off-chip memories, most of them are non-volatile, and they do come up with high density, but then you have a very negative point about it is that it has very high access time. Now, when you talk about all these kind of memories, of course, these are all made up of CMOS, and therefore they're highly dependent on CMOS scaling as well. So if you keep on, scaling down the transistor dimensions, you have to redesign everything, everything from the scratch itself. So there are a lot of issues involved with these CMOS scalings as well. Now, since I have discussed about about different kind of memories and different hierarchies in the system, now if you see from the perspective of a designer, he or she has to make huge choices. They have to find out among what kind of memories they are going to use, how they are going to use, and at which location they are going to use, and that makes the designs really very tough. So if you have too many choices, you really have to do huge amount of work in identifying which kind of memory to be used at which location or at which place. Now, taking all these things into consideration, most of the researchers who really do not want to make out the choices, they want to come up with some universal memory that has good characteristics of all these memories. So if you see SRAM, they are known for their speed. Now DRAM is known for its density because you can make out a memory element using just 1 transistor. So one transistor and one capacitor should be good enough to store the information, but then you, you have to refresh it every time. That is another story. But then it's important that its density is quite huge. So what people thought is that they should have a new universal memory technology that should have high density, that should have smallest footprint area, that should be non-volatile, it should have least access time, unlimited endurance, minimum leakage power, and also it should have some process compatibility. So given the fact that they have this all these kind of good things within them, so these universal memories can be really useful for them. And therefore, people started researching into different emerging non-volatile memories, especially spin transfer torque MRAMs, racetrack or domain wall memories, ferroelectric RAM, phase change RAMs, resistive RAMs. So all these, different kind of emerging non-volatile memories have been looked into very aggressively. And among them, before going on to other things, it's very important that we do understand the comparison of all these kind of technologies that we have off the shelf as on date. Now, the important thing is that you need to make a comparison between volatile and non-volatile memories. And when you make a comparison, you need to see that the SRAM and DRAM are placed within these volatile ones. When you talk about non-volatile memories, you have to make a comparison, which are in form of NAND flash, ferroelectric RAM, PCM, STT-M RAM. So all these, comparisons you have to make out between, before making a choice that which emerging non-volatile memory would be really good enough. So when you look into all these issues, the data retention, if you see for SRAM and DRAM, they of course do not have any data retention. As soon as you switch off the power, your everything is lost. Now, when it comes to the very non-volatile kind of memories, they do have the data retention that is quite sure about it. Now, when you talk about cell area, SRAM, as I said, it requires 6 transistors for realizing 1 bit of memory. So when you talk about cell area, the SRAM has something like 80 to 120 F square, where F is your feature size. Your DRAM would be standing something around 6 to 12 F square. Your NAND flash would have something like 2 to 5 F square. Your ferritic RAM has something like 15 to 35 F square, which is quite reasonable also in comparison to DRAM. Your PCM would have something like 6 to 12, and your STT-M RAM, which probably is really upcoming, is having something like 4 to 20 F square. Now, if you see, the STT-M RAM is almost overlapping on the lower side of your volatile memories. Right? So this is something which is really useful. When you talk about read access time, your read access time in your SRAM is something like 1 to 15 nanoseconds. Your DRAM has 30 to 60 nanoseconds. Your NAND flash has 50 to 80 nanoseconds. And your ferritic RAM has 20 to 80 nanosecond RAM. Now, when you go further, your PCM has something like 20 to 50 nanosecond of read access time. Your STT-M RAM has 22 to 20, which is again, on the lower side of your, of your SRAMs. So that way, if you see the area, the cell area, and the read access time, they are on the lower side of your, of your SRAMs. They're something which is really good enough. But when you talk about write and erase time, uh, again, the situation is quite better with STT-M RAM, 2 to 20, right, in comparison to some of the other type of non-volatile memories, such as 50 to 200. In your PCM, then your ferritic RAM 50, your NAND flash something like 10 is for 5 to 10 is for 7. Your write or erase time is 1 to 50. So that way, you can see that read access time or write erase time, they are on the lower side, right? And the cell area is also quite good enough. Now, when you go to read-write endurance, your rewrite endurance is really good enough for SRAMs and DRAM. That is something like 10 to the 16. And accordingly, when you go to NAND flash, you have something like 10 to the 5, 10 to the 9 to 12, so on and so forth. So all these things actually do help us a lot when we try to make a choice among different non-volatile memories which are available. Now, rewrite endurance, especially I would like to mention about the NAND flash, which is really very low in comparison to your SRAM DRAM. And when you talk about STT RAM, it's almost come to a comparable situation with that of your SRAM and DRAM. So this is really quite worth in comparison to NAND flash or any other memories that are coming up. As you move on with your standby power, of course, your volatile ones are going to have some standby power consumption, whereas your non-volatile ones, would be performing well in terms that they do not require any standby power consumption. Inherently, they have that property. Now, other than that, your read and write power is quite low, right, for STT, PCM, and electric RAM. When you talk about supply voltage, your SRAM, sometimes you can also operate in subthreshold voltage or subthreshold current region. So that way you can go down to very low voltages. So probably that limits, that puts no limit onto the lower voltage for this SRAMs. When we talk about STT-MRAM, it has to operate something around 1.5 volt. But now with better technologies, because what I'm discussing is something was available in 2013-14. But as on date, it is worth to say that as of date, STT-MRAM can also operate up to 1 volt of supply voltage. As far as product availability is concerned, every type is available. All of these types are available, but then they have some of the merits or demerits. But overall sense, if you see in form of performance analysis, your STT-M RAM does work really very well in comparison to any other non-volatile memories, or even I could say SRAMs or DRAMs in some way or other way. Now, taking it forward, once we are convinced that this STT-M RAM is really works very well and would be really quite useful, I think it's quite important as of now to see why the Spintronics and how the Spintronics actually works. So, what are the fundamental things which are there in place for these Spintronics kind of devices? So taking you forward into the introduction of your Spintronics, your electronics or Spintronics have certain, differences, some basic differences I would like to just put forward. Your electronics has a state variable which is charge of electron, whereas in your Spintronics, the state variable is spin of electron, right? So that is where you see the difference. Apart from this, most of the electronics is guided by classical properties, but if you see with smaller and smaller dimensions, you do need to look into quantum mechanical properties as well. But Spintronics inherently starts off with quantum mechanical property understanding. You need to understand these areas and then start working on to the devices as well. Now, if you look into the materials that are often used for electronics or Spintronics, yeah, electronics uses materials such as conductors, semiconductors, whereas for spintronics, you use materials such as ferromagnetic and non-magnetic materials. So the material type even that you use are quite different. Now, electronics has high power dissipation, that is true, but of course, the speed limitations are also there with different other issues if you try to reduce the power dissipation. But with Spintronics, of course, you have very less power dissipation, and if you design it properly, you can have higher speed also in comparison to electronics, especially your DRAM and other stuff. I won't say that it will be working very well or better than your SRAMs in terms of speed. But when you talk in terms of power dissipation, yes, of course, it is going to perform very well in comparison to SRAMs or DRAMs. Now, if you see furthermore, the basic attributes of spin, what are those basic attributes that you look into the spin? So if you look into all these basic attributes, electrons spin originates from its intrinsic angular momentum that it has. There are a lot of physics behind that. And the two spin states that it has spin up and spin down. Now in magnetic fields, your electrons which spin up and spin down have two different energies. And that is where, it becomes quite relevant to discuss all these things. Furthermore, now, if you look into spin transport, the basic operations that you can carry out is spin injection and accumulation, spin detection, spin relaxation. So all these things has to be there, once you're talking about the spin transport, right? So if you look into furthermore into all the details, your energy when you talk about for your upspin or downspin. For non-magnetic material, they'll be equally present, upspin and downspin electrons in the state. When you talk about the energy for downspin and upspin in ferromagnetic layers, they will have some difference, and that is how actually it makes a huge difference for the spin transport in these kind of systems. So I'll just take a small pause, maybe just for a second or a minute. Yeah. So I think we can go further into these basic operations, the spin injection and accumulation, spin detection, spin relaxation. All these basic operations have to be carried out when you're working with these kind of systems. Now, if you see the spin injection and accumulation, this is really very interesting to see. You have ferrometric layer on this side, which has in total some upspin, and a non-magnetic layer on to this side. Now, when you apply sufficient voltage across it, and if you try to see that there is some current that can flow through it, what you'll observe is the electron current, which is having equal spin up and spin down, they'll be filtered out by this ferromagnetic layer, and they'll pass on to this non-magnetic layer this way, right? And as you see that onto the junction side, you'll have more upspin electrons onto this side, and as you move far away from it, it goes down. So this goes down as you move away from the junction. And this clearly demonstrates how the non-magnetic layer can be injected with the electrons with one kind of orientation. So what you're doing in this process is you're injecting certain certain electrons with certain spin, right? So this is the phenomenon of your spin injection and accumulation, and this is very well demonstrated with the currents also. So if you see over here, you have a current which is equal to zero, and in that state, your ferromagnetic layer, would be having upspin and downspin in this form, and the non-magnetic layer, you have a balanced one onto this side with no net magnetic movement. Now, when you apply a current which is greater than zero, that is what we have been talking about. As you apply some current, you'll see that your the electrons will be shifting to the other side, and the net movement that you'll see in the magnetic movement that you'll see onto the other side, right, this way, and therefore you'll see a difference in these orientations also. So this is how you identify that the spin injection has been made onto this side. So very simple and very easy to understand phenomenon of spin injection. And next important thing is that how do you see the spin detection and spin relaxation as well. So the next slide shows you about the spin detection that can be done using your LLGS equation. That actually relates the magnetic moment or the magnetization with your precision torque, damping torque, and the spin torque. You just relate all these things, and all these things can really let you know that how the precision that will occur once you have this magnetic moment and H effective in place. You'll have three especially forces which are there. One is your spin torque, which will pull it out, then damping torque that will bring it, that will try to align this M with H effective. And if both of these things are balanced, spin torque and damping torque, you'll have a precision torque, right? So this electron will precess over here. And if you have enough spin torque, it will precess here and then finally switch to the other side. It can switch to the other side as well. And that is where you switch the memory from state 1 or 0. So we'll be looking into it much more in a much more detailed manner, right? But the important thing as of now is you need to understand how this LLGS equation is really important and how you can go ahead with these things further on. Now, if you go into the details, you can see a lot of physics behind that, and that would be really quite helpful in understanding the overall physics behind that. But then, being a electronics engineer, you need more understanding onto the circuit aspects, how it works and how it relates to your memory. Finally, how you're going to write it down, how you're going to read it out. So those things are really very important to understand. So before going into all those things, this is very interesting slide that you're seeing, the spintronic devices and magnetoresistance, which is quite easy to correlate and understand as well. So those who have gone through SRAM and DRAM details, right? Those who have studied those areas, I think it's very important and very, quite interesting to see how this simple, spin walls or GMRs actually relates to the different memory states. Quite easy and really understandable to make an inference out of it. Now, if you see the spin wall, you have three layers. One is your ferromagnetic layer, which can actually have orientations in either of the directions. And then you have another ferromagnetic layer at the bottom, which is again having a direction which is onto the one state only, right? So this is sort of a fixed layer, and this free layer can make orientations in either of these directions. Now, when you talk about giant magnetoresistance GMR, you have this kind of scenario where both of them are in the same orientation, right? The free layer and the ferromagnetic layer. As I told you, this can go on to the any of the states. So if you have this kind of scenario, you'll have, if you pass the electron through it, you'll have upspin. If you have the upspin electron, it will go straight away. Whereas your downspin will have, these kind of collisions and then pass it on. And if you have this kind of scenario where both of them are oriented in different directions, the electrons will have, either let it be upspin or downspin electrons, both of them are going to have some kind of collisions. And this actually results in two resistance states depending on the free layer orientation. So free layer orientation, if it is in this direction or in this direction, you'll have two resistance states also for the electrons. And this state is your parallel state where both orientations are in the parallel, whereas the other one is your anti-parallel state. And accordingly, the resistance would be the two RP resistance and the RAP resistance. There are two different values. And based on these two different states, you'll have GMR, which is RAP minus RP divided by RP. So that difference in the two resistance with respect to your parallel resistance, the lower resistance will let you know how much is the GMR. And this GMR you always will try to keep as high as possible. Now, this is quite important. Why would we like to keep it as large as possible, this GMR? So the very reason behind that is that you want to distinguish the two states, RP and RAP. That would be quite distinguishable if you are using, if you are using huge margin between them. So if the margin between them is quite small, you will not be able to distinguish the two states as well. So taking it forward, you need to understand how these GMRs are really worthwhile and how they are usable. So going further on, these GMR cells had very large size, and also they were having very small ratios also. So researchers started looking for some other alternative which actually worked, that could actually work on the principles of GMR only. And that is how they landed up with MTJs, magnetic tunnel junction. Now these magnetic tunnel junction are really very useful in terms that their size is very small. So you have free layer and the pinned layer. Right? So the similar structure as you had for your GMR, and this free layer and pinned layer is actually having a tunnel barrier in between, and then you have this TMR, right? Based on that. So TMR is almost similar to what you do with the GMR, right? So RAP minus RP by RP. But then one of the best things about these MTJs is that you could come up with very small size with a TMR ratio of something around 100%. Right? So people could land up even more than that. Typically, your TMR ratios as on date is something like 200 to 500. So that is really good enough. Now, this MTJ, if you see how it operates, you can have a operation where you can have free layer, right, and the fixed layer you can see over here, and then similarly you can see over here. And what you need to do is you need to write 0 or write 1. So these are the different states of these MTJs while writing 0 or 1 onto it. So if you write 0, you need to have a current which is greater than IHL, right? So once this current is greater than that, you'll be able to change the direction of this free layer. The fixed layer will remain same. If you pass the current, right from the bottom to top, if the current, if it is greater than ILH1 in this case, if it is greater than that, you'll be able to orient this fixed layer also. You'll be able to change the orientation of that layer also. So this is how actually you'll be able to change the direction of this current, and also the states of these MTJs quite comprehensively in this fashion. So this is what the state has been shown here. If the current is IHLO, greater than this, you'll be able to change the state from RAP to RP. And if the current in this direction is greater than ILH1, you'll be able to change the state from RP to RAP. So you can very well play with these devices, change their states, and store those memories for a very long time. That is what is important about these MTGs. Now, over the years, magnetic anisotropy or the type of MTJs has also improved, changed a lot. So you can see the two types of magnetic anisotropy, right, or MTJs in front of you. One is in-plane magnetic anisotropy, and the other one is interface perpendicular MTJs. Right? They have been put together here to make you understand, and you can see that this is having an orientation which is parallel to that of your MTJs here, and this is perpendicular to the to the tunnel barrier access, for this case perpendicular MTJs. So you have two types, IMA and IP MTJs. Both of them have been shown here, and they do have their own advantages and disadvantages. So if you see the disadvantage for IMA, in plane magnetic anisotropy, there are a lot of disadvantages in terms that they are all geometry dependent shape anisotropy, they have reduced scalability, require higher switching threshold current, and that is how actually it has huge power consumption as well. But one of the best thing about this is that it has high polarization. That is really good enough. But then if you are putting them in parallel, right, or in perpendicular, this is what you're showing here. If they are in perpendicular, the interfacial anisotropy starts dominating, and therefore your shape anisotropy becomes ineffective, and that is where you can scale down these kind of devices to much more extent. Other than this, it has lower switching threshold current, and also the energy requirement is quite less. But the disadvantage is that it has low polarization and high damping. So of course, everything do come with some good thing or bad thing, and that is what has been shown here. But as on date, your interface perpendicular MTJs have really become very popular. The very reason behind that is they can be scalable up to something like 10 nanometer technology node. So if you're able to scale down them to 10 nanometer technology node, it's really useful to integrate with your CMOS as well. So overall reduction in the size would be huge if you're using a transistor or a memory element form of MTGs that can actually be accommodated in a smaller piece. Now going further, what is the difference, how does this spin transfer torque negative resistance memory actually works? That is something which we need to look into and deliberate upon how it works. Now STT-MRAM, as I said earlier also, the spin-based MRAMs, they have actually now become a universal mode memory solution. Now STT-MRAM has not been, it's not that STT-MRAM came up recently. Your MTJs especially, which is one of the important constituent of your STT-MRAM, has been there for a very long time. So in fact, your MTJs were being used in read sensor of your HDDs also, hard disk drives. And these research had been carried out by certain researchers in France, and they could really showcase that if they are able to reduce the overall dimension of this MTJ, and also that translated to the overall reduction of the size of your memories also. So people could reduce the overall size by 500% using these MTGs because they could be used as a read sensor. So this STT-MRAM uses spin polarized current to write magnetic bits. It is non-volatile, random access memory with no moving charges. And of course, the key building block for all these kind of memories is MTG itself. Now, STT-MRAM has all the characteristics of universal memory, as I said. It is non-volatile as your flash memory. It is having a read or write speed comparable to SRAM. It has a density comparable to DRAM. It has unlimited endurance, and also it is highly scalable also. Other than this, your STT RAM has low power consumption. It has multi-level cell capability also, and that is where the STT RAM has been really doing very well. So once it has multi-level cell capability, you can store 2 bits of information using a single transistor, and that is where our group has been focusing a lot from last almost a decade now, where we have tried to see that using a single transistor we have showcased that we can store 4 bit of information, right? So this is recently accepted, and that uses a mechanism of STT and SOT both for increasing the storage capacity. And the overall power reduction is also quite reasonable using these kind of multi-level cell capability. Now going further, the spin transfer torque phenomenon, how does it work? That is really important to understand also. So you have parallelizing STT mechanism. If you have, if this is the state where both of them are in anti-parallel state, right? This is what has been shown initially. And if you apply some current which is spin aligned electrons in this case, and if these orientation electrons moves from this layer, goes through the tunnel barrier, and then it reaches here, which is an anti-parallel state, they start applying the torque. And if the number of electrons are large in number, they'll keep on applying the torque, huge torque onto this, and they'll be able to flip it. Or otherwise, if it is not number, either it is the number, so that relates to current, or it is the time. If it is there for very long time, they keep on applying torque slowly and steadily, they are able to flip this state as well. So this is how things move. And in anti-parallelizing STT mechanism, the similar things can be understood by applying the electrons onto it from the top. We apply the electrons, so the same orientation electrons will pass through, right? And then some of these electrons will be reflected back from the interface, and they'll start applying the torque onto it, some of them. And those who are having absolutely same, some most of them will pass on straight away. So you have different mechanisms for anti-parallelizing and parallelizing, all these kind of MTJs. So this is one interesting work actually that was carried out by some of the groups in 2003, wherein they have shown that the field-induced magnetic switching, how the FIMS MRAM can be made out, and this is one of the conventional MRAMs which people talked about. So it has a planar transistor you can see at the bottom, and then you have this FIMS MRAM, where you have an MTJ, and you have this bit line, word rate line, and they have this current which is being applied. They generate certain magnetic field also, and this magnetic field starts influencing the top layer over here, and once this free layer starts facing all these kind of external magnetic field, they normally flip their states as well. So this is something which is inducing the magnetic switching from the magnetic field which is generated from the current that you're applying on the easy axis. And then you have this hard axis current also, which keeps this fixed layer orientation as it is. It does not change at all. So based on this, you create an MRAM which keeps on flipping its state. Then came your one transistor, one MTJ STT MRAM cell, which was really much more useful in comparison to your FIMS MRAM, which was more dependent on the external magnetic field that you apply straight away. Here, actually, the things were very straightforward. You have your BL lines over here, and this is how the orientation has been shown. And this is where you have the storage element. And this is the transistor actually which applies the sufficient current, through these MTJs, which is able to change its state also. Now, what are the key advantages over conventional? So it has excellent write selectivity, it has high scalability, and this write current scales down with your cell size. It has low power consumption also. It has current would be something lesser than your 200 or 100 microampere. When you talk about the architecture, it's really very simple. It has no right line or no cladding. And when you go further into the faster operations, when you talk about, they also have multi-bit kind of writing compatibility. So you can write down multiple number of bits simultaneously. That is what I was talking about. The 2 bits or the 3 bits or the 4 bits that can be written or read altogether using very few number of transistors. So a lot of things going on and quite interesting also, I believe. STT-MRAM cell operations, as I said, this is something current that you have to apply from the top to bottom, and that will be switched on device using this transistor. And when you have to write, when you have to flip the state the other way around, you'll apply this current from bottom to top. So you need to ensure that the current either goes up or down using these kind of mechanism. And that is how you switch the states from anti-parallel to parallel or parallel to anti-parallel state. Now, when you talk about the read mechanism, the read mechanism was quite different in comparison to your CMOS one. This is quite different. But then, when you talk about its read mechanism, it's most of the non-volatile memories do have similar kind of equations. This is what I have understood over the time. So if you see the read mechanism, you have you have an MTJ over here, and then you have a reference MTJ over here. Now you choose this reference resistance in a way that your RP and RAP, the sum of these two resistances divided by 2, should be placed equally or exactly in between this RP and RAP. So once this RP and RAP resistance R reference is generated, then you start comparing the current that is passing through this MTJ. That will give you a fair idea about the resistance of this R reference. Now for read operation, current is required to be fed only in one direction. It's instead of what you do with your write, where you have to pass the current either from the top to bottom or bottom to up. But for reading, you can manage with one direction current only. And how do you do it? This is really very interesting to know as well. So you have this MTJ, it will have a state of either RP or RAP, and this reference resistance is sitting exactly in between. So if the current is higher, what will happen? The voltage generated Vx would be higher, and therefore Vx minus V reference will actually give you the resistance. So if you make a comparison between both of them, the RMTG and R reference, so if this Vx is large enough in comparison to V reference that you have created earlier, so if this voltage is, you can really understand that this is one which has been stored. And if this is RAP, which is different state, so what you'll do is, what you'll see is your R reference resistance is always in between, but then R MTJ resistance would be lower than your R reference. And what you'll see is this two states should not hold. So your resistance Vx, your voltage is Vx and V reference would be quite different, and that is how you can identify whether 1 and 0 has been stored onto systems. So these are some of the important things that you need to look into when you're working with spin-based memories, which actually lets you know how to go ahead with different read mechanism also. So this read mechanism, I believe most of you would have understood, and the same mechanism you can often use in your SRAMs or DRAMs also. So this mechanism is quite popular and has been there for some time now. Now going about footprint area of all these STT-MRAMs and how the footprint is and how big this footprint would be. So the footprint area of STT-MRAM, if you go into the details, the 6F square is a standard minimum. So footprint area, if you see STT-MRAM cell, you have something like 6F square, right? So you have two transistors here, and you have two MTJs, right? And so one MTJ, one transistor, the area required is 6F square. That is what we allocated in a minimum form for STT-MRAM cell. Now, if you want to reduce it further, if you want to reduce further the size of this MRAM cell, the best thing is to use a GAA or a smaller transistor, which is in form of GAA, which is called as gate all around transistor. Now, if you can see over here, the gate all around transistor is this one, and above this you have this MTG stack, which is going to store 1 or 0 onto it. Now, this MTJ stack is really very small in comparison to transistor still. So this small size of the transistor, although considered to be small in comparison to your planner, but still it occupies a larger area than what you would have expected using your planner transistor. So this work was carried out by our group in 2014, almost 7 years ago, and we could find that the overall area of this cell was quite small in comparison to your planar based transistors. So what we could find is that 33% of the area could be reduced using this GAA in comparison to your planar transistor. Instead of using a planar transistor, if you're using this GAA, we are able to reduce the overall area by 33%. And that is where you gain maximum out of it. And while we were reducing the area, the overall performance did not change at all. In fact, we had a better performance in comparison to the planar based transistors. Now, when we talk about STT-MRAM cell parameters or cell design parameters, your device level parameters are in form of anisotropy and graded constants. The parameters are physical dimensions, thermal stability, distance area product, optical switching current, tunnel magnetoresistance. So they are very different in comparison to what you see with your SRAMs. When you talk about cell circuit level parameters, they are again, write error rate, read disturb rate, sensing errors. So all these things, are quite different in comparison to your SRAM and DRAM. So this is how actually you see the difference between your STT-MRAM cell parameters, design parameters in comparison to your DRAM or SRAM, which has noise margins, which are very different. Then you have to see the pull-up ratios, pull-down ratios. All these things, parameters are different in comparison to what you see with your STT-MRAM. Now, if you see furthermore, the temperature voltage dependent TMR ratio, how does it change? Now, this is something which was really a big deterrent to most of the designs, most of the spin-based design um, prior to maybe 1990 or 2000. Now, although this research related to spin devices has been there for a long time, but if you try to go into the details, this research actually, which was conducted in something like 1980s, that translated into a device or maybe a material wherein you could see with the change in magnetic field, the resistance of that device or changed. That actually ushered a new area of spintronics. And for this remarkable work, Albert Furt and Peter Grunberg were awarded with the Nobel Prize in 2007. But then things did not move well because later on, because most of the devices that we had based on the Spintronics, they were highly dependent on the temperature, the ambient temperature on which it is operating. So if you see the TMR ratio, it drastically changes as you increase the temperature also. And I think it's very important to understand that the TMR ratio we cannot manage to change it too much, because if you're changing the TMR, that means the the difference between the two states is not really distinguishable. And once the difference between the two states are not distinguishable, probably you'll land up with different other problems as well. You will not be able to identify whether 1 or 0 has been stored onto it. So this is where you had this TMR effective for two different temperatures. You can see with 25 degrees centigrade, the TMR is big enough, which is in the red color. But as soon as you increase the temperature to 85 degrees centigrade, the TMR effective reduces drastically. And this reduction actually reduces the noise margins, the difference between the two states, so on and so forth. Now, going further, this Spintech 2015 released this first STT-MRAM bit cell array, right? And they could show that this STT-MRAM array, how they could create it using different one transistor, um, one MTJ storage cell. This is what the one storage cell has been shown here, and you keep on replicating it for making your STT-MRAM array. And you have this row decoder and a driver, column decoder and a driver, and a multiplexer placed over here, then the write block and read block, so on and so forth. So this is how the STT-MRAM cell array had been created. And this is the tape out that they had shown, which contained, each of these cells contained this transistor and MTJ put together. And that actually formed your MRAM cell. So the technology translated from material to device MTJ, and then from one device MTJ, it translated to a memory cell. And this memory cell is then furthermore, translated to a complete array, wherein you could store huge amount of information for a longer time without changing its content. So spin torque MRAM market perspective, if you talk about, it has increased tremendously. There are a lot of commercial production that has happened. The Everspin technologies is something which had started off quite early, and as on date they have a huge production also for STT-MRAM based memories, which which often competes with your DRAMs, right? And most of the designs that we have made out have been able to compete very well with DRAM especially. And most of the data centers that we have, they have replaced their DRAMs with these STT-MRAMs also, and that is really very fruitful in terms of energy perspectives. So the commercial production of all these memories is already there. You can see there are all a lot of companies such as Avalanche, Crocus, Cypress, Everspin, Fujitsu, Grandis, Hynix, Hitachi, IBM, Intel, Qualcomm, Samsung. So all these companies have jumped into the spin torque MRAM market perspectives. They are already there in the market, and they have huge perspectives in the future for the future development of memories as well. So you have prototypes in form of in form of 1 MB embedded memory or even bigger than that. And this trend has been continuing from time now. So you have from 2005 the Sony Corporation's tiny 4 KB kind of memory capacity at 180 nanometer technology node, and then with years, with different years coming up, the different vendors came up with larger memory capacity as shown. If you just Google this Everspin Technologies, this is one of the renowned companies. And now they have, as I mentioned, they have already replaced DRAMs at different locations quite comfortably. And in fact, all these MTJ based memory cells are also evolving very well. And in fact, many of these devices, STTM RAM, are being replaced by SOTM RAMs also, which is again a different class of memory. Right? So those cells are also coming up. So of course, all these things do come up with a lot of challenges. Challenges in terms of critical current density, how much current density would be required to flip the state of these, MTJs. Then your different MTJ models, then your PVT variations that you have to look into, the process voltage and temperature variations, then your read speed, your reference generation, fabrication of PMTJ devices in sub 50 nanometer regime. So all these things, have to be looked into quite aggressively if you want to perform, very well with these STTM RAMs. So prospects of STTM RAM, it's huge. It has huge prospects. Spintronics is of course a rapidly emerging area, and we can assure that the SRAMs and E flash. If you talk about especially E flash, beyond 32 nanometer technology, they will be replaced by these NVS RAMs. Yeah, and that is what you see in most of your laptops. They are coming with non-volatile RAMs as well. Now, DRAMs are also replaced in many of these systems beyond 28 nanometer technology node. And ultimately, it will replace the NAND flash also as a storage class memory beyond 22 nanometer technology node. So huge research has been carried out, not only in US, Korea, Japan, France, and Singapore, but many other countries. And the memory industry, as on date, is focused on substitution of on-chip SRAMs also next 5 years or so. Although it's challenging, but people are coming up with faster and faster memories. So I would say that MTJs are some of the basic devices as on date. If you talk about state of the art research which is going on, people are talking about MTJs being switched by laser pulses, and that actually is going to reduce the delay of switching a lot. And that way, the speed of these devices would be really wonderful, really much higher than what we expect with even SRAMs. So this is another class of device that we have. We have something around 10 minutes more. So maybe in the last we can have some question and answers related to these kind of devices as well. So spin orbit torque MRAM is another class of memory element that we have. So here you can see that you have this MTJ sitting onto this heavy metal layer. So you have this ferrometric layer which has an interfacing with heavy metal. So this is ferrometric layer on the top, which is the reference. Then you have on the bottom of this